We'll go ahead and I'm going to record this as well, so we have the notes on the videos as well for the second half of the circuit. Okay, so as a reminder, and like I said, just so I can get this on the recorded, we have another circuit that we're going to design based on a voltmeter. So we want our ranges to be 240 millivolts. We want 1 volt, 3 volts, 10 volts. The R meter and I meter is 60 ohms and 2 milliamps for that. So we'll just go through this step by step. And our first winner
Kately.
It does talk. It is a little creepy. Yes. Why did it not remove you? That's funny. Okay, so Kaylee, you are up first.
Okay, so I don't think I did this right, but so I took 2 milliamps times 60 ohms for R1.
For R1?
Yes.
Okay.
And so for R1 I ended up getting 60 ohms.
60 ohms? Okay, so it should end up with this, with right here. So the first thing you want to do is you want to find the voltage of your meter.
Okay.
Yeah, and you said R1.
Oh, shoot. No, I said range. Oh, no, I meant range 1.
Okay. So yeah, for the first thing that we want to do is we want to start in range 1, and then we want to find the voltage of our meter. Okay? So the voltage of the meter is equal to the current of the meter times the resistance of the meter. So we have 2 milliamps multiplied by 60 ohms. What does that give us?
1.20 millivolts.
1 point or
1.20 millivolts.
like that?
Although maybe I think I might have done the prefixes and units wrong, because I got 120.
Yes, 120.
Okay.
Agree with the 120. Like I said, the prefixes, you got to make sure when you type things in and then how they come out. So 120 millivolts or 0.212 volts. Okay, you okay with that? Okay. I'm going to go back. Honestly, I'm kind of curious to see how the computer pronounces all your guys' names. So.
Zach.
That's kind of uncomfortable.
It is uncomfortable. That was that first one we were doing. Okay, so Zach, now that I have the voltage across my meter, which is 120 millivolts, what's the next step?
I subtract the dash from the 240.
Okay. So VR1 is going to be equal to your range 1 minus voltage of the meter. Yep, because you're doing Kirchhoff's law. Because in range, we're going to start with the switch in range 1 and start with this position. All we have is R1 and the meter in the circuit. Maximum of 240 millivolts, maximum of 2 milliamps. Okay? So voltage from R1 is equal to 240 millivolts minus 120 millivolts. It's 120 millivolts. Okay? I think this is kind of where you were starting to go. I think you might have just jumped ahead on your notes a little bit. Okay. So we end up with 120 millivolts. Well, that makes it easy. Zach, I'm picking on you again since it's right here. So since we already know what the voltage is, what can we make the assumptions about? And they will be correct. What are the assumptions? Okay. Looks like something we have exactly right there. So R1 is equal to okay. Also to recognize, we have the same voltage, we have the same current. We already know what that resistance is. So if those two are the same, we know it has to be the same as something we've already solved. So if we get to that point where you have things that come out similar, it's okay to just, like in your calculations, be like, we have this current, I have this voltage, it matches what I had before, what I just solved for. Right there, there's my answer. Good enough? All right, so we have R1, 60 ohms. And we know at this point, we have 240 millivolts. Okay, everybody good to that point? Nope. Okay, Simon? Where did we lose you? So the 120 millivolt? Okay. So basically what we're looking at is we know that there's going to be a voltage drop across our meter because it has some resistance. We know we're going to get a voltage drop. We have to figure out what that voltage drop is. So in here we know the current, we know the resistance. So if we know current, we know resistance, we can get a voltage from that point. So then we just multiply those values together. Oops. And that gives us 120 millivolts. So then at that point we know, because this is the most amount of current we have, or can have, this is going to be the most resistance we have, this is going to be the max voltage that guy can ever drop. Okay? So then, once we know this voltage, we're going to come back and look at our different ranges. We got to find out how much voltage is going to be dropped across each of these other components. So we know we have a max of 240 coming in. I have 120 being dropped there. So what's left? The 120. And then the current, remember, going through a series circuit is always going to be the same. So if we have 2 milliamps of current flowing through here, we're going to have 2 milliamps of current flowing through R1. And since we have 2 milliamps of current flowing through here, we have 60 ohms. That's where we get 120, or we have 120 millivolts across R1 with the 2 milliamps. That gives us 60 ohms across, or that R1 has to be to maintain this relationship. If this was higher, if it had a higher resistance, this current would be going down. If we had a lower resistance, that current's going to go up, and then we're going to be breaking our meter at that point. So, like I said, so we have our set of parameters that we don't want to exceed. These are maximums. And then we build it to accommodate the maximum, and then anything less than that, it'll still work. Does that help? It is some practice, and that's kind of why we're going through these. Okay, so now that we have this value, let's move on to range 2, because there's nothing else we can do at range 1. Everything we have is solved. Everybody good? Before we move on. Okay, that's a little long. Like I said, I'm just playing with this program. I think I'm going to go back to the just the cheers. Okay. Yeah. Okay, Carson, next step. You don't know? Okay. 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 So now we're going to go into range 2. So we're going to erase this guy. We're going to come into here. Okay, so now that we move into range 2, we're going to look at what is our maximum voltages, what is our maximum current going through this. So in the circuit, we're going to ignore R3 and R4 because they're open-ended, they're not connected to anything, we don't care about them. So at this point, we have a maximum of 1 volt going in. What is our max current through this circuit? You got a ladder. Yep. The amp's going out. 2 milliamps. So at this point, we know that we have 1 volt and 2 milliamps of current. So there's a couple of ways we can go about solving this. So we know we have a total voltage, total current. What can we find with those two values? Total resistance. Okay, so when we find our total resistance, we could then subtract everything previous. Okay, that's one way to solve this, and that involves a few more steps. Another way to do it is just look at individually what's our voltage drops. So we know how much is being dropped across R1. 120 millivolts. We know we have 120 millivolts being dropped across our meter, right? So with those two combined, how much is that? 240 millivolts. We have a maximum of 1, so if from here over, we're dropping this amount of voltage right here. How much is left that we have to drop across R2? 760 millivolts. Because we have to drop 1 volt max. Okay, that's one thing that when we're doing through these, remember, this is the maximum voltage that we can have. This is going to be the maximum amount of current we can have before we damage our meter. Yep, it's Kirchhoff's voltage law. Every single time. Okay, so Carson, now that we have this, how much current do we have? 2 milliamps. So then, if we have 2 milliamps going through this resistor with that type of a voltage, what's our resistance have to be? $380. And it has to be, because we haven't done anything else to the circuit other than we've just changed the position on our meter to go up a bigger range. Does that make sense? Okay. So once we get to that point, we're going to continue doing the same thing. So now, Morgan. Yeah. Okay, Morgan, we are going to switch because is there anything else we can do at range 1? Or range 2, I guess. We'll switch to range 3, and where do we go from here?
So I did 3 volts times 1 voltage, 2 volts, and then you divide that by 2 milliamps, and then you get 1,000 ohms.
Okay, so real quick again, we have a maximum of 3 volts coming into the system. We have a maximum current of 2 milliamps because that's our limiting factor. So we have to drop 1 volt between these guys because we've already established that we are. That's the cool thing about these guys is once you've established that, it's always going to be dropping that amount. Yes, Simon? On the 760? Okay. How do we get that? So we have 1 volt coming in, we have 120 dropping here, and we have 120 dropping across our meter. So between those two devices, we have 240 millivolts being dropped already. So now we're coming in with more voltage. We can only drop the 240 there to maintain our limitations. So the rest has to drop across that resistor. There's no other place for it to go. And we want to design it so that that does happen. Does that make sense? Okay. So same with this one. We come in with the 3 volts. We know we're going to be dropping 1 volt of that 3 volts already on everything else. So we're going to take the 1 volt subtracted from the 3 volts. That gives us 2 volts across that resistor. Then we know the current is 2 milliamps because in a series circuit, the current's going to be the same everywhere, and that's our limitation. 2 volts divided by 2 milliamps is 1 kilo ohm. We good there? Kaylee, is that good for you?
Yeah, I'm still kind of having some trouble with the prefixing and everything.
Right. I mean, that's going to happen. This stuff's brand new to you guys, and it's, second week in. We've kind of introduced it for about a week and a half, maybe. It just does take some time to get used to. Okay. Read. All right. Yep, we're going to jump to range 4.
So I calculated the voltage for by simply minusing the 10 volts and only down to 3 volts.
Yep.
Set it by as well. After that, I used, see if I can decipher the I used the Ohm's law to calculate the resistance over R4 by dividing 7 volts, which is in shorthand the range of R4 minus R3 or 201. And I divided that over 2 milliamps, which is the current over R4. And I got 3.5 kiloamps.
3.5. Okay. Does that sound right to everybody else? So like I said, each one of these steps, as we move farther and farther back, you start on the very beginning and determine, okay, what do I have that can help me solve this thing? Well, the only thing I know I have is I have a maximum voltage, I have a maximum range, I have a current meter, or the resistance of the meter. With that, then I can calculate my voltage drop across this meter. And then I look at what has to be dropped in the rest of the circuit. So in the first step, all we had was R1, and it has to drop the rest of the 240 other than the 120. So what we're left with is the 120 millivolts. Then I know my current because I'm planning this as if it's full scale. So if we put 2 volts or 240 millivolts into this guy, we're going to have 2 milliamps of current. When I put 1 volt into this system, we're going to have 2 milliamps. When I put 3 volts, I'm only going to have 2 milliamps. When I put in 10 volts, I'm only going to have 2 milliamps. So the big thing to remember here is what has to change. If we're changing our voltage, but we're keeping our current the same, resistance has to change to maintain these ratios. It's Ohm's law. We have to have the changes as we're making changes. 2 things have to change. 1 thing can stay the same. That's how we're comparing all these. Yes.
So you said that a lot of times people will put like a potentiometer after to dial in your. So would that mean you just put like you only connect the first 2 leads and dial in just?
Yes.
Okay, gotcha.
Yep. You leave the excess lead off to dial everything in. So a lot of these guys, you could have this R1 could be 2 resistors, a resistor and a potentiometer. This one could be a resistor and a potentiometer. And you would go through and fine tune this thing until you got exactly what you needed or until it would calibrate to the system itself.
So could you measure the resistance from the beginning of R2 to the end of the potentiometer too?
Yep, and then that would be labeled as R2. Okay. Any questions before we go? Okay, sensitivity. Forgot that real quick. So remember, on your range, it's going to be the total resistance divided by the total voltage. So if we just picked this one to start with, so we have the 240 millivolts, how much resistance do we have in that range? 120 ohms. Yep. Because that's the total resistance. And we end up with So we end up with 500 ohms per volt. So this meter is half as good as the meter we previously designed. Kind of a common number to run into. You could do it for the rest of these as well. Pick any of the other ranges, add up all the resistors, divide by your total voltage. Okay. With that, you guys are excused. If you do have questions, please feel free to hang out and ask them. Like I said, I have my office hours today to be able to help you out with whatever you guys need too. So. See you tomorrow.